For exam 2, the chapters are 24, 26, and 27. We are skipping 25. It'll be on exam 3. You can still have a cheat sheet just like last time, whatever you want on the front of an 8.5 by 11 sheet of paper. You will also be given an equation sheet. I sent out that updated version earlier today. And what I think I'm going to do for this review is just quickly go into what I think are the most important bits of each chapter. And if there's questions, I'll expand on some of that. But otherwise, we'll be able to pivot straight to any questions that y'all have. So for chapter 24, of course, the main idea is what is electric potential, the amount of energy per unit of charge. So if you put a charge in a certain region of space, there will be a certain number of joules of energy available to it, a certain number of joules per coulomb of charge, and that doesn't depend on what charge you put there as far as how much is available to each coulomb of charge. It's what is around it. So what is the other stuff creating that potential field in order for something else when it's put there to have a certain potential energy. So that's the definition. But as far as calculation, it is good to know how work relates to electric potential. So that would be these two parts. And then how you would use that to apply conservation of energy, which probably a more direct example of that is not until a good bit later. So on this page, all of these questions are really good to take a look at. So applying conservation of energy between 2 points, if you know something about the equipotentials. Can you find the electric field based on the equipotentials? Can you see whether positive, negative, or zero work is being done based on the equipotentials? So on and so forth. And all of that can be answered much easier if you get the idea of that hill analogy, that positive charges like to roll downhill. In other words, positive work would be done on them when they're going downhill because they're speeding up. Negative charges like to roll uphill, so positive work would be done on them as they go from low to high potential. We can also say for positive and negative charges that if we're interested in the potential created by a positive charge rather than how it's responding to a certain potential, positive charge creates a hill, negative charge creates a valley. So we're sort of seeing both in this diagram. We could say that these positive charges, since we're interested in the potential they create, we would see as a hill. These ones we would see as a valley. Whereas if we release a positive and negative charge in that region of potential, they're like little marbles that are going to roll through that region. And so if I launch a marble through point B and it eventually ends up at point G, it will be faster at point G because it's going the way it wants to go. It will speed up. Whereas the negative charge, if I force it to go that way from B to G, it will still slow down because that's not the way negative charges like to go. So we're seeing both perspectives, experiencing potential and creating potential in that one. The other sort of calculation-y type thing that's important is questions like this. And for these, the main thing to remember is it's an easy calculation if you remember really two things. The first is that potential is a scalar quantity, not a vector, and so you don't have to worry about components for potential. You really do just add these numbers, even though at this point you're sort of conditioned to worry about vectors. This is finally a case where you really do just add. The other thing is you don't do an absolute value on these because the reason we did that before was direction, and potential does not have a direction. So we leave the charge as is. If you have a negative charge, you put a negative in. And then this addition literally means just addition. There's no x or y components here. That's the main stuff from chapter 24. I'm not going to grill you on the integral stuff. So let me see if there's some stuff I can cross out. This page you're going to want to have down because it just gets the analogy really clear in your head. This page has those examples. This whole page, I think it's safe to say we can rule out, except for maybe this was already written earlier, but it's spelled out a little bit more clearly here. the relationship between work and potential. Here, you don't need the derivation, just the actual potential created by a point charge, and then on the next couple of pages, you see how we add that. You don't need the potential of a dipole. You do want to know these properties of equipotentials. Went over conservation of energy. I will not have continuous charge distributions on there. Maybe this, not as a regular question, but perhaps something to do with a bonus. Not that. And then not this stuff, not the gradient stuff. So a pretty limited subset of chapter 24 is what I'm really expecting on the exam. 26. This is where we hand off from these local quantities, the electric field, and then some we introduce in the chapter, to the global ones like voltage, current, and resistance, the ones that are a little bit nicer to work with. Again, the analogy is a good thing to have in your head. This stuff up here is not so critical. Let's see, most important stuff would be, thinking back through everything I've got, directions of stuff is very important. So this question is a really good one to sort of have a feel for the exam. The calculation stuff, the only one that you might expect is one like that, where it's just stringing together a few different equations to figure out how long it takes an electron to get from one place to another. But that's about the extent of calculations that I can think of, and then resistance versus resistivity. So we come down to that. No temperature dependence, but the relationship between resistance and resistivity, and then what resistance is, and then Ohm's law, that is on there. So that's a good example for that, as is this one. Power would show up in a question about an actual circuit. So I would give you a circuit and I ask you about the power dissipated through a particular resistor. So this does show up, but more in the context of chapter 27. So just remember you've got several different ways to calculate power dissipated, and then it is mostly plug and chug. The only thing to be careful about is, and I think it gets restated in 27, this statement only applies to a particular resistor, meaning you have to know the current through that resistor and or the voltage across it to apply any of those equations. If you don't know that voltage, you only know a battery voltage or something like that, you either got to find that voltage or use a different equation. And then, let's see. Remember what Ohm's law says, which is not just that V equals IR. That's actually a definition of resistance. That's just we decided to call V divided by I the resistance of something. What's special about Ohm's law is the observation that a lot of times that ratio is a fixed value. Even if you turn up the voltage, you have a bigger battery, you will get a larger current out that is proportional. So if you double the number of batteries you use, you're going to double the current you get out for a lot of materials. Not everyone, but a lot of them. And that's the main stuff for 26. So again, not the different types of velocity, but directions of field, current density, drift velocity. Calculation could be something like this one, where you're stringing together a few of those different quantities to figure out travel time. And then other calculations could be relating resistance and resistivity. Other conceptual type stuff could be about Ohm's law. What is the difference between resistance and resistivity? That kind of thing. Impedance plethysmography, it's not on there. I don't think you were worried it was, but just to be sure. And then this is all derivation. The main thing is just that stuff in the box. So that's chapter 26. All right, 27. We are not going to do anything with internal resistance, meaning every battery is an ideal battery on the exam. So you don't have to worry about the difference between V and this fancy E, but the difference is the fancy E is the amount of work done by the battery per unit of charge. V is the amount of energy you end up with per unit of charge. Because it's not a perfect world, there is some waste in that battery, in the internal resistance, and so not all of the work that it does ends up as energy that can be used in the circuit. That's all that this is saying, and in particular, this right here is just a claim that things aren't perfect. We're not going to get out quite what we put in or what the battery is putting in. And if we look at that on a per Coulomb basis, per Coulomb of charge, then we get that relationship. But for the sake of the exam, we assume they're the same thing. Whatever it says on the battery is what you have as your voltage. Loop and junction rule. You will need to do one problem with that as far as finding currents by applying the loop and junction rules, meaning the last problem in this chapter, something along these lines. But like here, where I just sort of gave you the numbers at the end rather than going through the painful algebra, all I'm going to ask you to do on the exam is set up the equations that you need. So 2 loops, tell me what the equations for those loops would be. If you have a way you've learned in circuits that's a little bit different from the way we've done it in here, do that way. As long as it's consistent and gets the right answer, I'm fine with it. It's a little extra work to figure out all the extra negatives and stuff, but it's fine. Just do the way that makes sense to you. This is probably not a bad thing to put in a cheat sheet, just saying. Let me come back up again. So that's Kirchhoff's stuff. These are the general kind of conceptual ideas of them. You can expect more calculation stuff with Kirchhoff because the conceptual is the nice part. Why would I be nice? Series and parallel, know what the difference is between them and how to recognize them. So series, same current. Parallel, same voltage. The book says something like pair V and series I or series Q, which I think is nonsense. But if it helps you remember it, they say like, all right, parallel, same V, series, same I. Or if you're talking about capacitors, you usually talk about charge rather than current, so series Q. But to me, that's just, I don't know, it looks weird. As far as calculations, though, expect not to have something that's just 2 resistors in series or parallel, but a combination. So a question more like this is reasonable to expect, but toned down a little bit. And I think that's the main stuff for 27. So series versus parallel, applying Kirchhoff's rules, finding equivalent resistance and current leaving a battery using the series and parallel relationships. Nothing about internal resistance is on there. And then the rest of this stuff is derivation. So really, as usual, if it's in a box, it's probably the important stuff. All right, questions for chapter 27.
Voltage division will be covered, right? Or
Not in this sense, not as like application stuff, but there are some things that just end up being a voltage divider because you've got some stuff in parallel and some stuff in series like a voltage divider is.
okay, and then for the last question about the junction and current, you said only to set up the equation, correct?
Yes.
Okay.
And for that one, the junction rule is actually going to be a conceptual question, meaning I sort of give you a picture and ask you to tell me something about the currents. So they come pre-labeled. You don't even have to worry about that step of like, well, which is the right way, even though there isn't a right way to label them as far as solving the problem. I'm going to give you a direction for all of them and ask you what would the equation be for those directions of current flow. All right, so that's a recap. If you need me to go over any other bits of that or anything in more detail, let me know, or if there are specific questions on the review that you would like me to do. Either is an option now.
Actually, for chapter 26, will we also go over the current density or?
Insofar as it shows up in, it's a direction you need to know. So current density direction is which way an electric field would make positive charge move. And so another way to think of that is if you can figure out the direction of the electric field based on what you're given, it's the same as the current density direction. E and J are always in the same direction because E is in the direction a positive charge would feel a force, J is in the direction a positive charge would move. And then calculation wise, only so far as might show up in a problem like this. Does that answer the question?
Yes, thank you.
Mm-hmm. Okay, what other
Um,
questions?
so I have a question. I'm actually driving home and I'm on my cell phone as far as connected to the meeting, so I cannot see any of your like screen or whatnot.
Okay.
But um, we covered it last class, I believe. At the end, there was the longer circuit problem. Don't necessarily know how to describe it, but it was where we found all like we worked the entire circuit out at all the loops and
Yes.
everything. I can't remember. Is that chapter 25 and therefore won't be on the test, or is that on the end of 27? Which one was that?
That's the end of 27.
Okay,
Yep.
and I obviously I can't see or know anything, but if you wouldn't mind, could you work an example out of that from the review so that I can go back and watch it and see it? Because I just would like to see that for a second time.
Sure. Yep, I can do that. All right. So I'll get to that here in just a little bit. What other questions are there?
I have a question on the exam review on number 4.
Okay, let
I
me.
remember seeing it, I think, on one of the assignments. I can't remember if it was the graded practice or the homework, but I'm not really sure
So this
if I
one,
got the right answer.
this one right here?
Yes.
Okay.
Yes.
So the guiding idea here is you could either just plug and chug of the work done between 2 points is negative the charge times the change in potential. But I think it's more intuitive to kind of look at what the electron is doing in as far as going uphill or downhill, and then say, okay, is that going to speed it up or slow it down? So let's see. For path 1, this electron is going from 50 volts to 80 volts. So is it going uphill or downhill?
Uphill, right?
Yes. Is that what it likes to do or not what it likes to do?
It wants to do that.
Yes. So this is 30 uphill. That would be something that does positive work, speeds it up. So we're comparing not only the change in potential, but also is it something that's going to want to speed it up or slow it down? All right. Then for path 2, tell me about the change in potential and whether that's what the electron's wanting to do or not wanting to do.
It would want to move in that direction too.
Yes, and it goes up by 10 volts. Is that going to lead to a greater speed or a lower speed than in case 1?
Would it be less because it's less distance? I mean, more because it's less distance? Or
So it's less distance for it to speed up over. Think of it as it's easier to imagine positive charge because it does the thing that makes sense. It's something rolling 30 meters downhill versus 10 meters downhill. The thing rolling 30 meters is going to speed up more because it's gone a larger distance to gain that speed.
that makes sense.
Okay. And then we look at path 3. So what has it done overall?
It's gone uphill, right?
Yes, by 20. And so you could even think of this as it went downhill, sure, but then it went right back uphill. So it's like those two parts don't really matter. They cancel each other out as far as when it was going this way, that was going to be doing negative work on it, slowing it down, but then it speeds right back up going the other way. So all that really matters is what's left over. And then for path 4, what did it do?
It went uphill, but eventually it went downhill.
Yes.
But would it overall be like how you said earlier, how those two, like it did start off going downhill, but it started going uphill, so those cancel out. Would that same apply towards the
Yes.
end?
Yeah, so it went up by 10, and then it went up by another 10, but it went right back down by 10. So you could think of it as you were climbing from 70 meters to 80 meters elevation, sure, and then you went from 80 to 90, but then you came right back down to 80. So effectively, you're only 10 meters higher than you started. And so all 4 of these would serve to speed up the electron, meaning do positive work on it. But we see that in case 1, it's going to be the most work, followed by case 3, I think, and then 2 and 4 tie. Is that what I had as a solution?
I think it was D because it was going from least to greatest.
Oh, least to greatest. Yep. So I would have gotten that one wrong on a knee jerk. Yes, that I agree with that ranking. And then we could check it also with this equation. The reason this works out just the same is because it's negative Q0 delta V. So negative, an electron's charge is negative, and then delta V. So all that really matters is the sign of delta V, because this stuff is positive. So the bigger delta V is, the bigger the work done.
That makes sense. Thank you.
All right, other questions? Because that one with the equivalent circuit is going to take a little bit, so I want to make sure I address some maybe smaller questions before I do that one.
Could we go over 15 for chapter 24?
Yes.
Because I don't really get the like distance.
Okay, so like how I got the distances?
Yeah, like I don't understand like what counts as, because I think on the either the homework or the one of the assignments, it was like, yeah, it was like D versus 2D, and I wasn't sure how to like qualify which is which.
Okay. So for distance, always remember it's straight line distance. So if I want to find the distance from this point to Q1, it's that length right there. If I want to find the distance to the big Q, it's that distance, and so on for Q2, Q3, and Q4. So all I'm doing to get all those square roots and stuff is just deciding, am I given that distance or am I going to have to find it? So for the distance, say, to the big Q, I realize, okay, it's this distance from there to there, but that's half of that overall length of this square. And so that is a length of D. So this distance is D. But for the diagonal, now I see that it's, this is D, this side is also D. So this is, by Pythagorean theorem, D squared plus D squared, take a square root, or square root of 2D squared, or square root 2 multiplied by D. So I took D out of the square root. And similar for the other four. Does that make sense?
I think so. It's just like using the Pythagorean theorem.
Yes.
Is like the best way.
Yeah.
Okay.
So a case where, just to give another point, where you might use, pretty much it would be either D or square root 2D in this problem, because like if there were another charge right here and we wanted to find its distance to the center point, that would still be D. But in general, it really is just think about where is your charge. So if we have some collection of charges, or we want to find, say, what is the potential right here, then it's not like any sort of trick on what the distance is. It's, all right, this is the distance between that point and this charge, and then that point and this charge, and then that point and this charge. And those are the distances that would go in that KQ over R formula. It's just, if I need to do extra math to find those distances, I will. If I'm given those distances, then I won't do extra math. Sometimes people would, because they're given these two distances, automatically try and do the Pythagorean theorem with those, but you don't need it, because all that really matters is the distance from those charges to that center point. Okay, other questions?
Sorry, is number 16 something similar to number 15 then in terms of what we're doing?
Similar, but a lot more work.
Okay.
So it is not only finding the potential at that center point, but using it to say, if I send an electron in from infinity, which is just to say from really far away, where it was initially at zero potential, and it ends up at whatever the potential is here, how will its speed have changed? So it's sort of like combining this problem with that one we did up here, to say, like, not only is the potential it's seeing changing, but that's going to change the speed of the electron, and we want to know by how much. If I hop back over to the solutions for that, you can see it's a little bit more involved.
I see that it's mostly just plugging and chugging at the end with...
Yeah, the main observations really are that, here, I'll use the laser pointer for once. We had to find the potential at the origin, because that's where the electron's moving to. We're told it's at zero potential initially. And then we applied conservation of energy. and the rest is plug and chug. All right, I'll jump to one of those equivalent circuit problems. So strap in, this is going to take a little bit. We have a 12-volt battery. R1 is 1.4 ohms, R2 is 2 ohms, R3 is 6 ohms, R4 is 2 ohms. We want to find the current through resistor 2. So ultimately I want to know, I don't even know if it goes this way for sure, but ultimately whatever the size of that current is what I want to know. Now that I've read that, I'm going to forget that immediately because it doesn't matter. I'm going to just start doing the process and eventually that'll fall out. Same with how much power is dissipated by resistor 3. If I know everything there is to know about the circuit, then I don't have to worry about how to find anything because I already did it all. I would first look for series and parallel. My advice on that is to go for the ones that in your gut are the strongest candidates for series or parallel. Sure, it might kind of feel like those two are in series, but I know that these two are in series because there's nothing else in between to get in the way. So, if I start with that and then simplify my circuit down, it will become obvious what to do next after that. If I try and combine all of them in one step, I may do one wrong because I thought stuff was in series, because in fact, these two are not in series because you got this junction in between. So that's my first step, is to say this is in series, and so series equivalent 6 ohms plus 2 ohms is 8 ohms. All right, I redraw my circuit. And yes, it is very tedious to do this every time. But you also get it right. So I think it's worth it. When you can get it right without doing this, feel free. All right, so we're down to, this is 8, this is 2, this is 1.4. And so again, I look at this and I say, well, it kind of looks like these are in series, but I'm pretty darn sure these two are in parallel. And I can do, again, to be honest, I just see it and my brain screams parallel, and I don't know that I ever had a way to know, but the way I've come up with that maybe helps is that pinch test. So I imagine putting one index finger here, my other index finger here, thumb here, thumb here. Let's see if I can draw some sort of monstrosity that gets that idea across. Okay, so I've put my fingers like that and thumbs like that on the bottom, and I can pinch my fingers and thumbs together and they'll meet at a junction. Or, depending on how quickly I pinch, they could meet somewhere here, but they can come together without running into something like, for instance, if there were a battery right here, I wouldn't be able to do that. My finger and thumb would get stuck on the battery, if you want to think of it that way. Or even if it was another resistor, I'd have to do something with that before I could apply this. So I see that there isn't anything else. It really is just those two resistors, and so they are in parallel. And that's the one where I have to do 1 over 1 over. You may have seen you can do product over sum. That only works if it's two resistors. Otherwise, you got to go back to this. Like if I had 5 more things in parallel, I'd have to do 1 over plus 1 over, and so on and so forth. That multiply the two and add them thing only works if you've got exactly 2 resistors in parallel. 1/2 is 4/8 plus 1/8 is 5/8. So this is 8/5. Let's see, 1 3/5 maybe. And so I can replace those two with a 1.6 ohm resistor, not change anything up here. So 1.4, 1.6, 12. And finally, it is absolutely clear that those are in series. I don't need to think about that at all. So series 1.4 plus 1.6, that's 3 ohms. And so one final one to draw with a single resistor. And that makes it very easy to determine the current. because current for a single resistor is the voltage across that resistor over its resistance. I've only got a single resistor. I know the voltage across it is 12 volts, 3 ohms, so 4 amps. And so I can put that on every picture now. That's what leaves the battery. But I'm not done because it asked me for the current through resistor 2. So I got to keep working for a little bit. The next step is to find out everything else there is to know about the resistors in this circuit. I know the current through both because they're in series. It's the same current either way of 4 amps. So now I need to find the voltage across each. Well, to find the voltage across a resistor, I need the current through it and its resistance. I know the current through it. I know its resistance. V equals IR. So that should be 5.6 volts. And that's the voltage across the 1.4 ohm. For the 1.6 ohm, I could add little subscripts here if we want. For the 1.6 ohm, same idea. And it's the same current because they're in series. So that comes out to 6.4 volts. 6.4, 5.6. And I can carry that up here as well because it was the original resistor, not an equivalent. For these two, though, it's not the current that is in common for both, it is the voltage. These are in parallel. They must have the same voltage across them as their equivalent resistor. And then I need the current through the 2 ohm. Well, I know the voltage across it. So current through 2 ohm. It's V equals IR yet again, but I solve for current, so V over R equals I. 6.4 volts over 2 ohms should be 3.2 amps. And I can do the same thing for the 8 ohm resistor. I know the voltage across it. I know its resistance, so that should be 0.8 amps. And as a check, 4 amps go in to this junction. I calculated that 3.2 amps come out through this branch, 0.8 amps come out through this branch. That better add up to 4, and it does. Similar down here, 5.6 plus 6.4 better add up to 12, because it's like stair steps down through each resistor. So I've finished question 48, because it was about that current. It's 3.2 amps. But then how much power is dissipated by resistor 3? I don't think I'm quite there yet, but I'm almost there. So let me go back to my original circuit and see what I've got. I know this is 4 amps, 5.6 volts, 6.4 volts. I do still know this is 3.2 amps, 0.8 amps. And I think that's everything I can carry up from previously, because when I look at this, it was actually a series combination of 2 resistors. So whatever current there is through it is the same as what was through my series combination. So 0.8 amps goes through both R3 and R4, but I don't know the voltage across either of those until I calculate it. So the voltage across 3, 0.8 amps, 6 ohms, that should be 4.8 volts. And then across the 2 ohm, 0.8 amps times 2 ohms is 1.6 volts. Those better add up to 6.4 volts, because that's what I had across my equivalent, and they do. 4.8 plus 1.6 is 6.4. The final step is, if I want to know how much power is dissipated, I got 3 different ways to calculate that. IV, V squared over R, or I squared times R. I know everything there is to know about that resistor, so it doesn't matter which one I use, I'll get the same answer. But my general advice is, if it's going to take less work to just find the current and use I squared R, do that. If it's going to take less work to find the voltage and use V squared over R, do that. In the rare occasion where IV is the easiest way, it usually isn't, because you usually know the resistor value and either the voltage or current, but in that rare case, use IV. So you don't really have to choose if you solve everything, but if you want to be a little lazy, then just pick the one that makes you solve a little less. But anyway, looks like we got the correct answer, 3.2 amps, and then 3.8 watts. I found the right voltage, I found the right current, so I'm thinking that's going to work out too. All right, other questions?
I think for the series in parallel, you said that that's what will just be on the exam, that reducing the circuit enough to get it to where we have to find certain components, like you just did with the current, and then use that for the power, correct?
Yes.
Okay.
Yep.
Could you go over number 46, perhaps?
46, sure. Okay, a set of light bulbs are connected in parallel to a 120 volt source. Each dissipates 60 watts. Current has a fuse that burns out, or circuit has a fuse that burns out when the current is 9 amps or greater. Determine how many bulbs you can use without burning out the fuse. So, the idea here is you've got a bunch of stuff in parallel. Parallel means same voltage, currents add. So if there's 120 volts from the wall outlet, or you've got a 120 volt battery for some reason, but presumably a wall outlet, that means you've also got 120 volts across this battery and this one and however many others you care to attach in parallel. That would be like you have a big power strip and you plug in lots of light bulbs into that one. Eventually you could see it would probably blow out because you're asking for too much current. The reason being, we can see how much current goes through this based on how much power it is using. We can see how much current goes through this one and through this one, but where is that current coming from? The battery. And then it's just splitting off bit by bit as you reach each branch. And so you end up with a little less after that branch and even a little bit less after this branch. But it's because each little bit is kind of going off along to one of the light bulbs. So let's figure out how much current is going through each light bulb. If they dissipate 60 watts of power, well, this is that one case where it is kind of convenient to use IV because I want to relate the current and the voltage. Reason being because I want to figure out the current that blows the fuse. Just that's why we're looking for current. So current is power over voltage, 60 watts over 120 volts. So 0.5 amps passes through each light bulb. And so, how much current would the battery or outlet or whatever it is provide if we had only one light bulb? Say none of those were there. We only had one light bulb. How much current would have to be provided by that wall outlet?
Could you just divide it by 3?
Well, here's the thing. This is similar to, I think it was a homework question. When you plug something else into your wall, does everything else get dimmer?
No.
No,
No.
because they're in parallel. The current demands of one thing have no influence on the current demands of anything else. So I've got one light bulb now. It's still dissipating 60 watts because it's got the same resistance as before. It's still going to have half an amp flowing through it. But for each additional light bulb that I connect, I'm asking for an additional half amp to be able to power it. And that's why if you plug too many things into an outlet, it's bad, because you're asking for too much current and the breaker will trip. So with one light bulb, a half amp. What about with two light bulbs?
So that would just be 1?
Uh-huh. What about how many light bulbs would require 9 amps?
About 18?
18 bulbs is what would ask for or require 9 amps from the outlet. So if I pull 9 amps from the outlet, that's going to be 9 amps to the fuse. It burns out at 9 amps. So I got to go one less to be safe. And that's where I get the 17 from, right? So largest number that can be used without burning out the fuse. If I actually had 9 amps flowing, it would burn out the fuse. So the best I can get away with is 8.5 amps used. Other questions?
I think for the voltage division, you said we could just use that general, like, global formula where it's 1 over that 1 over R. But do you mind if we also use that special formula where it's only two resistors?
No, I don't. But also you can't blame me if I give you three and you do it and then you're like, why did you count me off?
Okay, so I'll just stick with that general formula that we're given then.
Yeah, I mean, I'm not gonna force it. If you get the right answer, you get the right answer. And it is a valid mathematical thing, but just to show where it comes from. So 1 over R1 plus 1 over R2. If you want to get a common denominator in the bottom, multiply the first one by R2 over R2. So R2 over R1, R2. Multiply the second one by R1 over R1. That's not changing anything because it's 1. Now you have 1 over R2 plus R1 over R1, R2. Or take the reciprocal, R1, R2 over R2 plus R1. So that's fine. But what if you had 1 over R1 plus 1 over R2 plus 1 over R3? Well, then to get a common denominator, that would be 1 over, I got to multiply first by R2, R3 over R2, R3. Second one by R1, R3. And then third one by R1, R2. And then you have the common denominator, but I mean, I think you can see it's a little rough. R1, R3 plus R1, R2 all over R1, R2, R3. You're dividing by a fraction, multiply by the reciprocal. R1, R2, R3 over R2, R3 plus R1, R3 plus R1, R2. And if you had 4, it would be that and another set of terms. But anyway, feel free to use whichever as long as it makes sense and it gives the right answer.
Okay, thank you.
Yep.
On the homework, I don't know if we have anything like this, but there was a question that basically was asking about the potential difference across two sections of wire and then the rate at which thermal energy is lost. Are we doing anything like that?
Could you read it out in full?
The figure shows a resistor of resistance 6.13 ohms connected to an ideal battery of 12.5 volts by means of two copper wires. Each wire has length 21.5 centimeters and radius.
I remember now. So yes and no. Yes, in the sense that the hint for that one was treat the two wires as just additional resistors. And then it's really just asking you to analyze this problem and compare it to if you just treated those as zero resistance, so pretended these were short circuits rather than the wires having any inherent resistance. So yes, in the sense of series resistors is a reasonable thing to ask. Yes, in the sense that resistance is resistivity times length over area. No, in the sense that I will not combine those into one single question.
Okay.
Let me, for once I actually have the exam ready at this point. It's rare, like really, it's very rare, but let me pull it up so I can check that I've not missed any gotcha sort of stuff. We went through talking about finding the total electric potential, some stuff with conservation of energy and work and all that, if you know something about the equipotentials. Directions of stuff for current density, current electric field, resistance, resistivity, combinations of series and parallel, Kirchhoff's rules, and then I like the bonus. I'm happy with how this bonus turned out. You may not be, we'll see. But I don't think there's anything I really missed talking about or bringing up.
Mr. Wade.
Yes.
Sorry, one more thing. You said we only needed to know the definition of EMF, correct?
You
I
don't need to
think-
know like the internal resistance stuff and that it's technically a little bit different than voltage.
Oh, okay. That's
Yeah.
what I wanted to know.
In fact, I mean that's really something that was never stressed to me when I learned physics too. So I like to point it out to say like, look, here's why your battery's not working as well as you'd think it would based on the label. But it's not essentially on exams we can almost always pretend batteries are ideal. Questions from anyone else? All right, well, if there are no other questions, we can end a little bit early. And if you do think of anything in the meantime, feel free to email. And I will see y'all tomorrow for regular class and then Thursday for the exam.